Thank you very much, Carol, for the kind introduction and for the invitation to come here. I'm going to be telling you today about some work done with a number of really outstanding collaborators. Now, I'm going to right away break one of the second most important rule in comedy, which is that if joke's not funny if you have to explain it, and you shouldn't have to explain jokes, but I'm going to go ahead and explain this one. The name of this talk is Thermalization and its Discontents, which is a play on this book of Freud's, Civilization and its Discontents, which made the point that the things that people instinctively and selfishly would like to do are in conflict with the things you need for to have a society that's functioning. Like you see a car that looks nice and you'd like to just steal it, but you can't have that in a society, and because if everyone went around stealing, that would be chaos, and so you have to kind of suppress your primal desires. Or to give another example, something that we'd all love to have would be time crystals or topological phases at temperatures greater than 0. Whoa. Okay. And those are in conflicts with the thing you need for a well-functioning society, which is thermal equilibrium. Okay. And so what I want to talk about today is really the tension between the cool stuff we'd like to have, subconsciously at least, and the stuff that we need to have a functioning society. Now, why is thermal equilibrium so great? Well, in thermal equilibrium, there's this quantity, the entropy, which is maximized. Or equivalently, it means that when you have a system in contact with a bath and you maximize the entropy of the entire system plus bath, you have a free energy that's minimized. Okay? The minimization of free energy allows you to compute the values, or at least the expectation values, of physical observables x using the partition function, or trace e to the minus beta h. And then by studying trace e to the minus beta h, you deduce that you can have phases of matter, which is to say that as you change the parameters in the Hamiltonian, the observables change smoothly as those parameters are varied, and then not smoothly, in some non-analytic way, in the thermodynamic limit, when those parameters are taken across a phase transition. Now, those phases of matter, for instance, are, to give examples, they're phases of matter characterized by spontaneous symmetry breaking, which has with it associated rigidities, generalized rigidities. More recently, there's been a lot of excitement about topological phases of matter, which to some extent can be thought of as at least partially protecting quantum information, and that is its own kind of quantum mechanical generalized rigidity. To give some examples of the firsts, which is spontaneous symmetry breaking, a crystalline solid is an example. The equations describing the interactions between the atoms in a solid are translationally and rotationally invariant, but the ground state and low energy states are not. They actually spontaneously break that symmetry. That spontaneous symmetry breaking causes crystalline solids to be rigid, so that, for instance, you can imagine people resting on a metal, which is a crystalline solid girder high above the streets of New York, and apparently not having to worry about it too much, because, of course, they are all aware, as you can see, that they're intimately aware of the fact that the spontaneous breaking of the translational symmetry gives a rigidity, because if the translational symmetry is broken one way here, there's an energy penalty to break it differently, which is to change the length of those chemical bonds somewhere else. And that energy penalty causes it to be rigid. On the other hand, if you don't break those symmetries, like if you just have a gas, then you have no such rigidity. And as Wile E. Coyote is going to discover here, well, gases don't have the rigidity of crystalline solids. And as soon as he looks down, the symmetry will be restored, and he's going to fall. Other examples of spontaneous symmetry breaking, well, pneumatic liquid crystals. Those break rotational symmetry, and they're essential for LCD displays. They rely on pneumatic liquid crystals. Superfluid helium also is a broken symmetry state of matter. That's a little more abstract, the type of symmetry that's broken. It spontaneously breaks global gauge symmetry, which is related to the conservation of the number of helium atoms. A ferromagnet spontaneously breaks the spin rotational symmetry. The ferromagnet is made up of constituents which carry small magnetic moments due to the electron spin, essentially. And although their equations are rotationally invariant, they spontaneously choose some direction. Now, around 2012, the following question was asked and a proposed answer was given, which is, okay, we have all these broken symmetries. Can you spontaneously break what is perhaps the most fundamental of all symmetries, which is time translation symmetry? Okay? And Wilczek, and in subsequent analysis, Al Shapir and Frank Wilczek together proposed or coined this term time crystals as a state that spontaneously breaks time translation symmetry. Now, the idea is that just as superfluid helium breaks this global gauge symmetry, and an Ising ferromagnet, for instance, breaks a spin symmetry, and a spatial crystal breaks translation symmetry, that there might be a state of matter that just breaks the time translation symmetry that any system with a time-independent Hamiltonian conserving energy has. Now, it turns out that that can't happen in the ground state of a system. Okay? Because if you have a system, a quantum mechanical system in its ground state, well, the ground state, or in fact any energy eigenstate, the way it transforms under time translation is it just, the state just acquires a phase. Okay? E to the I times the energy of that state times t. And so, since phases themselves are unobservable in a state of the system, that phase doesn't change any physical observable, and as long as you're just in the ground state, you can't have any breaking of the time translation symmetry. There's no observable which will look different at one time than at another time. Okay? But then it was thought, well, okay, so just looking at the ground state maybe is not the right way of looking at it. Perhaps one should look at some correlation function with the ground state, like a 2-point function. Measure the ground state at time 0, measure it again later at time t, and let's see if the ground state was sort of primed to break the time translation symmetry so that this 2-point measurement shows some non-invariance under time translations. Well, it was shown by Watanabe and Oshikawa that in fact that can't occur either. And moreover, not just as a ground state property, but in thermal equilibrium also this can't occur. So if you compute the thermal equilibrium 2-point correlation function, you can never get something that depends on time in some non-trivial way. Okay? And the basic reason, which is to say that depends on the time at which you measure this. And the basic reason is if the positions are very far apart, okay, as you would expect if you're breaking some symmetry, if you take the positions far apart, this expectation value has to decompose, okay, and just by locality of the system, and then it's the product of two things. And since the Hamiltonian e to the minus beta h obviously commutes with the Hamiltonian itself, which is what does time translations, those are going to have to be equal, okay, those two expectation values. So time crystals cannot occur in thermal equilibrium, including zero temperature, which is thermal equilibrium, which is the ground state. Okay. So if we're going to have time crystals, so this is the sense in which I said this is sort of thermalization as discontents, which is that thermal equilibrium just rules out the possibility of time crystals. So we're going to have to go outside of thermal equilibrium. On the other hand, that's a little bit scary. And also, not just scary, it makes you think that, well, this is not going to go anywhere interesting because, after all, once you go out of thermal equilibrium, lots of stuff can happen. You don't particularly, thermal equilibrium just is very different. And it's almost too easy to get things that have time dependence out of equilibrium, right? So yes, some aspect of that definition is too restrictive. It seems to be the fact that it's thermal equilibrium, or the assumption that we're in the ground state or in thermal equilibrium. But going out of equilibrium makes it too easy, so we have to be a little careful, okay, and be very careful about the way in which we go out of thermal equilibrium, okay? Because it's easy to get time dependence. Just think of Rabi oscillations. Take a spin, put it in a magnetic field, and as long as the initial state is not in the direction of the magnetic field, you will see Rabi oscillations, okay? Because SZ is going to oscillate, okay? But that's not really broken time translational symmetry and analogous to a solid. This is just kind of a trivial time dependence coming from the fact that you're in a superposition of two eigenstates, okay? On the other hand, it's also easy to avoid this kind of time dependence. Okay? So whatever we do, we better not allow, if we're going to come up with a definition of a time crystal that is not restricted to the ground state or thermal equilibrium, we certainly shouldn't count something like this as a time crystal, right? This is obviously not what we're talking about, okay? Or you could say, well, let me just take a pendulum, okay? Pendulum, let it go, it's going to oscillate, okay? It's some trivial oscillation. It's not a ground state property. It's also easy to get a pendulum not to oscillate. Just let it hang straight and it's not going to oscillate. So again, you don't want to include something like that as time crystal. This isn't a phase of matter. It doesn't have the same rigidity that like a crystal does, or an abstract analog of the rigidity associated with crystals or superfluid healing or something. So we don't want to include trivial stuff like that. There's some slightly more non-trivial kind of borderline cases, like the A.C. Josephson effect. Okay, I don't want to get into the details of those, but actually those are, and there are driven versions of that, driven Bose-Einstein condensates that are kind of analogous to that. They sort of have some of the aspects of time crystals that I'll discuss later, but really the primary phenomenon in systems like that is that there's some other broken symmetry. Like the A.C. Josephson effect is piggybacking off the superconductivity, the driven BC off of the Bose-Einstein condensation. And so we'd call this some kind of epiphenomenon here, okay, where really there's some other physics. So, and in particular, if you explicitly break that other symmetry, the time crystal is gone. So if we are going to have to venture outside of thermal equilibrium, but in so doing, we had better keep in mind that out of equilibrium, there's lots of things that are time dependent that are not really phases of matter, okay, in the normal sense. And we certainly don't want to consider those. Okay, so in going out of equilibrium, what we're going to do is we're going to focus on, okay, a particular class. So thermal equilibrium is too restrictive, but it turns out, and I'm going to explain how there do exist non-equilibrium systems that have all of the quote-unquote good features of thermal equilibrium systems, okay? Which is, as we discussed thermal equilibrium systems, thermal equilibrium has this concept of the entropy, which leads to a free energy, which is entropy maximized or free entropy minimized. You have phases of matter and so on. So there's an enormous amount of statistical mechanics and intuition associated with it that we can draw on in thermal equilibrium, which you just don't have in general outside of equilibrium. The point here is that there do exist non-equilibrium systems that have all these good features, okay? And in fact, they have that in a very simple way, which is that there exists some time-dependent basis change. Okay, so if you apply unitary transformation to the Hilbert space of the system, or in other words, if you go to some kind of rotating frame, they actually look just like systems in thermal equilibrium. Okay. So that's, in some sense, a very minimal kind of departure from equilibrium, because yes, they're not in equilibrium, they're not in thermal equilibrium, but there is some kind of essentially rotating frame in which they look like thermal equilibrium. Okay. And because there is some other basis, which in general is kind of hidden, you don't a priori know what it's going to be, I'll call such systems in crypto-equilibrium, meaning hidden equilibrium. So it's a system that's out of equilibrium, and the examples we'll look at are like very, very far from thermal equilibrium, but they have, in essence, they have a kind of hidden equilibrium, which when we analyze them, we'll see that if looked at in the right way, they're just like equilibrium systems. Okay? And it turns out that in crypto-equilibrium, time translation symmetry can be broken. And time translation symmetry actually is a symmetry just like any other symmetry, just like spatial translational symmetry, spin rotational symmetry, or what have you, which is not the case in thermal equilibrium. Okay. So just to make that point one more time, the definition of crypto-equilibrium is that there exists some possibly time-dependent unitary transformation that transforms a time evolution to that of a system in equilibrium. Okay. Let me explain. I'll give some specific examples, but let me explain how this happens, okay, that there are systems in crypto-equilibrium. Most of them, in fact, almost all of what I'm going to talk about today is actually periodically driven systems. Okay? So that's clearly well outside of equilibrium. So these are systems I'm going to initially at least consider closed quantum systems that are being periodically driven. So they're being periodically shaken in some way, or you're applying light to them at some frequency, for instance. And for such a system, closed quantum system, this is what Schrodinger's equation looks like. Okay? You have a Hamiltonian. That Hamiltonian is time dependent. Time derivative of the state vector is the Hamiltonian acting on state vector. Okay? And such a system has eigenstates not of the Hamiltonian, because the Hamiltonian is time dependent, so the eigenstates of the instantaneous Hamiltonian are not really the things that we're most interested in. But what it does have is what are called Floquet eigenstates. Okay? The Floquet eigenstates are eigenstates of the time translation operator through one period. Okay? So just as you would use Bloch's theorem in k-space, in momentum space, to understand wave functions inside of a spatial crystalline solid, Floquet eigenstates are the analogs of Bloch states. They are periodic functions in time, okay, multiplied by an exponential piece that tells you the eigenvalue under translation by one period, where this t here is not the temperature, but is the period of the drive. So the drive, the Hamiltonian, is invariant under translation by capital T, and the Floquet eigenstates are equal to functions that are also periodic under period t, multiplied by some exponential that changes by a phase. And that phase that it changes by is the Floquet eigenvalue, sometimes called the quasi-energy. It's not the energy. The reason it's not an energy, and the reason is that this is only well-defined up to 2 pi time divided by the period. So another way of saying that is the energy is, there's a quasi-energy that's conserved up to multiples of the period of the drive. So the system can absorb 1, 2, 3, n photons, okay? And its energy can change by multiples of that frequency, 2 pi over t, okay? But only by that. Okay, so mod 2 pi over t, there is a well-defined quasi-energy, just like an electron in a crystal has a quasi-momentum. Okay? Same idea, but this time in frequency rather than momentum. Okay? And this operator, the time translation operator, through one period is often called the Floquet operator, and the Floquet eigenstates are the eigenstates of the Floquet operator with eigenvalue e to the I epsilon. Okay? So these are, in periodically driven systems, the analog of energy eigenstates in a time, in a time-independent, undriven system. And we can understand the property. Now, the thing that's interesting is because these eigenvalues are defined only mod 2 pi over t, there isn't unlike in a time-independent system where there's a lowest energy state. If you have no time independence, there's a lowest energy state. It's the ground state. It's a very special state in the spectrum. As you cool the system down, you go to the ground state. But in a periodically driven system, there's no lowest energy state, right? Because you may look at some state, you think it's the lowest energy, but there are states that you think are higher in energy, but of course they're equivalent to each other up to subtracting 2 pi over t. And so really that you should think of the states as the eigenvalues as living on a circle given by this phase. So there's really no preferred place in the spectrum, unlike in an undriven system. So when we try to understand the states of the system, unlike in undriven systems where we can say, well, let's just understand the ground states of the system, here we kind of have to understand generic states of the system. And it's useful to understand generic states of the system to compare generic states of a Floquet or driven system with generic eigenstates of an undriven system. Okay? So let's imagine we have a closed quantum system, and it's in an eigenstate, either if it's undriven in an energy eigenstate or if it's driven in a Floquet eigenstate, epsilon. Okay? And let's consider, in order to understand this generic eigenstate, let's consider a subregion, A, within that system. The subregion A is assumed to be large, but much smaller than the total system. Okay? Then we can form reduced density matrix for that subsystem. Of course, the whole system is in a pure state, epsilon, but if we focus on that subsystem, trace out all the other degrees of freedom, we have a density matrix for that part and an entanglement entropy for that density matrix. Okay? Now, in a sense, the rest of the system out here is acting like a bath for this part of the system, and that's kind of the intuition you should keep in mind in thinking about this. Or at least it can form a bath for this. It turns out there's basically two possible things, three, as we'll see momentarily, things that can happen. Actually, up until about 10 to 15 years ago, really people thought there was just one thing that could happen, modulo some special cases, which was the often called the eigenstate thermalization hypothesis. For a static system, this just means that if I take a generic excited energy eigenstate somewhere in the middle of the spectrum, nowhere near the ground state, let's say, middle of the spectrum, which is where most of the states of the system live, I form this reduced density matrix. It looks just like a thermal density matrix. It's just e to the minus beta h. H sub a is just the Hamiltonian restricted to my subsystem. And the basic reason is the rest of the system is acting like a heat bath, and so it's just like a system in contact with a heat bath. It has a thermal density matrix. The temperature beta is determined by the energy of this energy eigenstate. Okay? And this basic idea was formalized as the eigenstate thermalization hypothesis by Deutsch and Schrednicki. Okay? Now, this is, in essence, this is the reason why we can just as well use the microcanonical ensemble as the canonical ensemble in StatMech, because you use the microcanonical ensemble for closed quantum system in an energy eigenstate, and you get the same answers in the canonical ensemble, because in the microcanonical ensemble, if I'm looking at any local properties, the rest of the system is acting like a heat bath just as it does in the canonical ensemble. Okay. Now, around 15 years ago, it was realized that there is another possibility, which is called many-body localization. Now, many-body localization occurs in systems in low dimensions, so 1 and probably 2 dimensions, okay, that have a lot of dirt. They're very disordered, dirty systems. And in such a system, because of all the impurities that are in the system, actually the impurities localize all the excitations in the system. And as a result, the outside of region A is not able to act as a heat bath. In fact, if you compute that entanglement entropy, unlike here, where the entanglement entropy would be proportional to, where the entropy associated with density matrix rho would be proportional to the volume of the system, as it would in thermal equilibrium, here instead, it's proportional to the surface area of the system. The localization allows entanglement only to build up across the boundary between A and its complement. And so this is very, very far from thermal equilibrium as a result of the localization caused by the impurities that prevent entanglement to occur between distant regions. They can only occur across the boundary. Now, it turns out, basically, periodically driven systems repeat the same classification, which is to say, if I take a periodically driven system, the generic situation, okay, is that it just absorbs energy and heats up to infinite temperature. So if I form the reduced density matrix, okay, then the reduced density matrix is just the identity matrix. That's a thermal density matrix at infinite temperature. Okay. Now, of course, there are exceptions to this. If the system is actually in both the static and the Floquet case, if the system is integrable, there are extra conservation laws that may prevent stuff. For instance, including, obviously, non-interacting systems like free fermion systems or something. But the generic case is system absorbs energy, heats up to infinite temperature, and the physics is kind of boring. Okay? But it turns out that again, if there's a lot of impurities in even our periodically driven system, then it's possible for the periodically driven system also to undergo many-body localization. In that case, the system doesn't heat up to infinite temperature, and what it instead does is it only can build entanglement just across its boundary because of that fact it can't actually absorb energy from the drive. Basically, the local excitations of the system, if I look at the system locally, the local density of states has a discrete spectrum, and if the frequency of the drive doesn't hit one of those energy differences, which in general it won't, that in particular, if the frequency of the drive is high, so that it's higher than any of those local energy differences, then the system just doesn't absorb any energy. Okay? It doesn't heat up to infinite temperature and stays way out of equilibrium and just has a area law for its entanglement entropy. Again, even though we're far, there's not in a ground state or anything like that. Okay. Now it turns out, as I said, there actually is a third case, which we've come to appreciate a great deal in the last couple of years, which is sort of a subset, actually, of this case, okay, but an interesting one. And this is called prethermalization. So it turns out that even in a system that satisfies the eigenstate thermalization hypothesis, and if it were driven, would heat up to infinite temperature, it may actually take a very, in fact, exponentially long time for that to happen. In static systems, that can happen. You may have exponentially slow thermalization due to the emergence of an approximate symmetry. That sort of the simplest and best laid example of that occurs when one parameter in the Hamiltonian is much larger than the others and basically acts as a dynamical barrier, preventing the system from thermalizing. In the case of Floquet systems, if the frequency is very high, then in the high frequency limit, there's very slow heating. The heating is exponentially slow in that frequency. Okay? And so even though this system will indeed heat up to infinite temperature, will absorb energy from the drive, there's a very long period of intermediate period of time called the prethermal regime, which actually gets exponentially long as you increase the frequency. And in that intermediate regime, the system doesn't heat up to infinite temperature and actually, as we'll see, acts a lot like a system in thermal equilibrium when viewed in the right rotating frame, and has interesting phases of matter and non-trivial physics. Okay? And so part of what I'm going to be discussing today is interesting phases of matter here when there's impurities in many-body localization, and interesting phases of matter here. Now, you might say, well, okay, is this really a phase of matter? I mean, this thing is going to thermalize and go away. And the answer is yes, it is eventually going to thermalize, but only after an exponentially long time. Okay? So these are the cases of crypto equilibrium. And as I said, this thing, yes, it's going to equilibrate and be boring, but only after an exponentially long time. And you know, in the long run, we're all dead anyway. So if something happens exponentially later, let's not worry about it. Okay? Okay, so what can you get in crypto equilibrium? So as I said, one thing is time crystals. Okay? And let's, for a moment, imagine that we had a orchestra playing the second movement of Dvorak's New World Symphony. Okay. Okay. But they were just playing the first two notes over and over again. Okay. A, C, and then rest. And then A, C, and then rest, and playing it over and over again. Okay. Now, of course, if you listen to them from the beginning, you would know what they were doing. But it's also possible, okay, that, and let's imagine now that we had many orchestras playing the exact same thing. Well, if you listened and you just tuned in halfway through, you wouldn't actually know if they were playing the two notes and then resting, or resting first and then playing the two notes. Okay? And they could, in fact, be playing this instead. Okay? And even worse, you could have a situation where some part of the orchestra, or one of the orchestras was playing this, and the other orchestra was out of phase. Okay? And you would end up hearing both. Okay? Now, if most of the orchestras were playing this, this would obviously be louder, but you would hear a little bit of this. Okay? And so you might get scared that you had a shark after you, first of all. And you might also wonder, how come they're playing out of phase? And the answer is that, sound waves don't interact strongly. Okay? They just add. So if you have one set of musicians playing out of phase with the others, you're just going to hear both. And it's going to be a little bit of a mess. Okay? So you're going to hear all of this music, and then you're just also going to hear this. The sound waves are just adding. But what if, okay, and now of course in real life, the musicians kind of look at each other and interact. They see each other. They notice that they're not playing together. But if we imagine that they were in soundproof boxes so they couldn't hear each other and they couldn't see each other and so on, you would have this problem. It would be really nice and really interesting if they could self-correct, okay? Meaning, not that the musicians would self-correct, which generates a lot of entropy for the musicians to self-correct, but if the sound waves could just interact. And if the sound waves could interact, then the part that's out of phase would get damped out by the majority and go away by the end. And that self-correcting property is characteristic of spontaneous symmetry breaking in thermal phases. Okay. For instance, consider spontaneously broken discrete symmetries, like lattice symmetries, translational and rotational symmetries. Consider graphene, honeycomb lattice of carbon atoms. Methane can be absorbed on it. Okay? And you could imagine a situation in which the methane chooses half of the lattice sites to sit on, but spontaneously chooses which half. Okay? Now, of course, you could get a shift. Locally, either one is just as good energetically. But if you shift one relative to the other, then you actually create a domain wall. That domain wall has an energy cost, and that energy cost suppresses reverse regions that are out of phase with the bulk of the system. Okay? And that suppression of those kinds of fluctuations is what causes a self-correction in systems that break symmetries. Okay? Now, of course, this is a simple picture. In reality, there are fluctuations. Right? Even in the perfect crystalline state, there'll be fluctuations. You'll get some misaligned regions. But because of the energy cost associated with that domain wall, you will preferentially fluctuate away from having misaligned regions. And on average, the methane will stay on the same half of the lattice. Okay? In the liquid state, on the other hand, where there's no preferential region, you might look, if you take a snapshot, you might see in the liquid state, by which I mean the liquid state of the methane, you might see small regions that momentarily look crystalline. Okay? You take a snapshot, it looks like a crystal. Okay? But if you look on average over long time scales and over the whole thing, although small regions momentarily look crystalline, on average, the probability for the methane to be on one or another half of the sites is equal. Okay? So it is a little subtle, the distinction between a solid and a liquid, because the liquid, if you look at a snapshot, it actually looks crystalline. And if you've ever done a belly flop into a swimming pool, you know it can look really hard and solid on short time scales. Okay? Conversely, so the liquid may look crystalline. You have to look over long time scales and over long distances to distinguish. And conversely, like I said, the solid state, the crystalline state, may look liquid because there are momentary fluctuations. But again, that you average out and preferentially they go away. Okay? And just to illustrate how hard it is to tell whether something is solid or liquid, I'll show this video. This is a swimming pool. And what's been done with this swimming pool is they've poured custard into it. Okay? And basically, you'll see this is now a swimming pool. And on short time scales, I said, where these short time scales are now a bit longer than just belly flopping into a swimming pool, you can see that as you step and walk onto the custard, it's actually pretty solid on short time scales. Okay? You can walk right on it as if you were walking on water. Okay? But you'll see that when he stops and stands still, okay, he's walking. When he stops and stands still, he starts to sink in. And he's sinking deeper and deeper because, in fact, this is not a solid. It's a liquid on long enough time scales. And actually, he's got to be kind of careful because to get out, he better not make any sudden movements, because if he tries to pull his leg out suddenly, well, he's stuck essentially in a solid. Okay? So really, the distinction between a solid and liquid isn't actually that easy, and you really have to check, because something that looks solid may actually be liquid and vice versa. So our self-correcting sound wave oscillation would have to be like methane on graphene, where you've chosen one half of the sites would be like this way of playing the music, and playing out of phase would be like choosing the other set of sites. And if you ended up playing both sort of equally, that's like a liquid where there's equal probability to be on any of the sites. Okay? And so that's what we are looking for is some kind of self-correcting property. Okay? Now, what that means in terms of time translation symmetry is a little subtle. I'll give you now a precise definition. So intuitively, it's that it should have this self-correcting property and that the system should choose spontaneously to play this or this. And once it's chosen, usually by the initial conditions, once you've chosen this, any fluctuation that would tend you toward this will get damped away, and you'll stay with this. Okay, that's kind of intuitively what we want. To make that precise, okay, there are two ways to do it. One is, we'll say that TTSB is time translational symmetry breaking. It occurs if for any initial time t1 and initial state psi, where the initial state should be short-range correlated. And by short-range correlated, what I intuitively mean, there's a precise definition, what I essentially mean is any state that you can prepare from a local product state in a short time. Okay? So take a state where, let's say you had a spin system where each spin is not entangled with anything else, and any state you can prepare in a short time for that. So these are basically physical states. What you don't want to consider as your initial state is like a cat state, like a Schrodinger's cat being superposed between dead and alive, because that involves building up huge amounts of long-range entanglement, and that's not a physical initial state. So because after all, that would decohere very rapidly anyway. So given any physical initial state, which is a short-range correlated state, there exists an operator, some operator, meaning some measurable thing, such that if I measure at later times, that operator is not invariant. The measured value of that operator is not invariant under a time translation. Okay? Even though the Hamiltonian of the system is invariant under this time translation t. Okay? So this is a little bit like, if I think of like the Ising model or system in double well potential, it's basically saying, look, if I put on a tiny symmetry breaking field, no matter how tiny, the system wants to have all spins up like this. And in this case, the analog of that tiny symmetry breaking field is the choice of initial state. Okay? That determines whether you play AC rest, or the reverse. Another bit more formal but very compact one is that time translational symmetry breaking occurs if the flow k eigenstates cannot be short-range correlated. Okay? A way to think about that is, look, the flow k eigenstates, after all, are the eigenstates of the flow k operator. They necessarily have trivial time translation properties because they just change by phase. Well, if they just change by phase, those are states that do not show non-trivial time dependence, so they better be states that can't be prepared. They are not physical initial states. So it's really saying the flow k eigenstates are unphysical states, and all physical states show non-trivial. All, not just ground states, after all, it's a periodic-driven system, all physical initial states show non-trivial time translation symmetry. And that actually is analogous to, again, if you consider the Ising model, if you consider their eigenstates of the Ising model, let's say in a finite but large system, transverse field Ising model, finite but large system, and if you consider the eigenstates of the Hamiltonian that are also eigenstates of the spin-flip symmetry, then it turns out that the ground state is a superposition between all spins up and all spins down. And the lowest excited state is all spins up minus all spin downs, and those are both cat states. They're really not physical states, and they're split by a tiny amount exponentially large in the system size. Okay? And so that's, in a static system, how symmetry breaking occurs. It's that the symmetric states are unphysical states. They're cat states. Here it's the same thing, except that there's no extra symmetry other than the time translation symmetry. So we don't have to say the eigenstates of the Hamiltonian and of some symmetry. It's just the eigenstates of the flow k operator. Okay? So in that sense, both of these are very natural, in some sense, straightforward generalizations of the way we define formally translational symmetry breaking in static systems of ordinary symmetries other than time translation symmetry. Okay. 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 So let me then give you a theoretical model of such a time crystal, which we call a flow k time crystal because it's occurring in a periodically driven system. That system has a discrete time translation symmetry, but that time translation symmetry will be broken spontaneously. So we're going to start out with, let's say, a chain of spins, just some microscopic magnets like we often do in the Ising model. Here's our spins, okay? And what we're going to do is we're going to manipulate those in two ways. So we're going to have a time-dependent Hamiltonian. And what that time-dependent Hamiltonian does is, first, for some period of time, it applies a field that rotates these spins. There's a field into the plane of the board, and that field rotates these spins. That field is going to be enough to approximately rotate the spins by 180 degrees, but not precisely. It doesn't have to be a precise pi pulse. Something 170 degrees, 172 degrees, something approximate. Because after all, this is going to be a stable state of matter, and we shouldn't have to tune anything in a state of matter. Okay. If you make it too far away, if it rotates the spins by like 90 degrees, then you're going to be outside. You've crossed the phase boundary. But we'll apply a field that kind of approximately rotates the spins by 180 degrees. Then, after a period of time, we turn off that field, and we just allow the spins to interact ferromagnetically. Okay? So in this case, I've drawn the ferromagnetic interactions as not being just nearest neighbor interactions, but also including second neighbor and third neighbor, with interactions decreasing as some power law, because one of the systems we'll be considering has long-range, power law range interactions, which is one of the experimental systems. But it works just as well, maybe even as simpler, with just nearest neighbor interactions. Okay? And at the same time, we'll apply a random, in this direction, magnetic field. Okay? Random meaning from one side to another. It's random, but it's not changing in time. Okay? And then we just repeat. So this is one cycle of our periodic Hamiltonian. We do this for a little while, we do this for a little while, then we go back and repeat. Okay? So it's a periodic manipulation. The period of the Hamiltonian is t, so here's t, 2t, 3t, and so on. We break that period into two pieces, t1 and t2. During the first interval in each period, we do this approximate rotation. During the second interval, we let the spins interact and subject them to this periodic magnetic field. And then we repeat with every period. So it's a periodic in time Hamiltonian. Okay? What happens? Okay? Start from some initial state, do this periodically, what happens? That's the question. Okay? I'm going to give you the equations that correspond to those pictures. Okay? So here is the, I've written it down for you here as an exact rather than approximate. This is an approximate, this is an exact 180-degree flip, but it doesn't have to be exactly this. I can just put some variable g here, where g is close to pi over 2, or theta, which is close to pi over 2, but not necessarily equal. And then the next piece over here in the flow K operator is just time translation under the action of some Hamiltonian, where that Hamiltonian, so here is our, here I've written as an exact, but there's also, it could just as well be an approximate pi pulse. Here is evolution under some interaction between spins I and j, as well as a random static magnetic field. Okay? So this is just the equations that go with the pictures I showed you on the previous slide. Okay? And these kinds of models have a history going back to work in the late 90s about thermalization and so on and so forth, and continuing up into the recent years. Now, what happens? Well, okay, so we start out with some arbitrary configuration. We rotate it. Let's say we do a rotation by 170 degrees. So we rotate all these spins by 170 degrees. Okay. Then we let the spins interact, okay, and subject them to this random magnetic field. The interaction, now these spins can interact, and maybe two of them can flip together, exchange their spins, and now they've been scrambled a little bit. We now rotate them again, not by 180 degrees, but by 170 degrees. Okay. So now they've done two 170-degree rotations, so they definitely haven't come back to where they started. And don't forget, they had some interaction, so they could, the spins could exchange and so on. And then you let them interact again. So now you've gone through two periods, and you can see that the spins have not returned to how they started. And after one period, they were not flipped from where they started because we did a 170-degree rotation, and we let them interact with each other. Okay? So yeah, we keep doing this. Okay? And what happens? Okay? What you might think is, well, with all these 170-degree rotations and all these interactions, they just forget the initial state and just wash out. And the spin, if I look at any spin, its expectation value in any direction is just 0. Okay? You might think that. Okay? Or, well, maybe they point a little more strongly in one direction and have some amplitude point in other directions. But with all these 170-degree rotations and interactions, you don't necessarily expect anything special at late times, that this thing's just going to get scrambled. Okay? Is that what happens? Well, if that were to happen, that would be an example of a way to get a liquid state, okay, an analog of a liquid state. You sort of forget all of the initial state. You scramble it out with these 170-degree rotations. Okay? And if I look at time n times t after n periods, I get the same as what I get in the next period. Okay? Again, it loses all of the initial state and it just kind of washes out. If I measure like halfway through a cycle, of course, I'll see something different, but it kind of all washes out. Okay? And that's analogous to the liquid state of methane on graphite. If I look at any site, it's equal probability. Okay? Just like you have an equal same state here and here. Okay? Another way of saying that is if I look at a spin on a given site, okay, then there's some short time. Remember, I'm doing these approximate pi pulses, I'm doing these 170-degree rotations. So on short times, if I look at even and odd times, so these are the even times, these are the odd times, they're going to be approximately opposite because of these 170-degree rotations. But after a short time, that all gets wiped out, and even and odd will be approximately the same. And for what I showed you earlier, the spin expectation value, in fact, this value is 0. But there's nothing special about 0. It might not be 0. They might end up pointing on average in some direction. But the same at even and odd times. And then eventually at very late times, T star, the system will just heat up. Okay? Possibly. Okay? But there's another possibility, which is that there is some initial time transient behavior in which you forget some of the initial state. But then there's a very long region here, this prethermal regime, which in the case of many-body localization, if there's enough impurities in the system and the dimension is low enough, this time goes out to infinity, and so this never ends. And there's now an alternation between even and odd. Okay? That is what would be a time crystal if you had that kind of alternation. And for that to occur, what you need is stronger interactions in step 2. When that occurs, you do this rotation by 170 degrees, and things are kind of flipped, but not exactly. They interact. Those interactions, as it turns out, stabilize the system. Now you rotate it by 170 degrees again. You didn't quite go back to here, because you rotated by 340 degrees. But those interactions kind of stabilize stuff. You interact some more, and you keep going. And at late times, it hasn't forgotten all of what was happening in its initial state. Some of it is decayed away, but not all of it. And what happens is, when you go from step n to step n plus 1, you actually rotate by exactly 180 degrees. Okay? Now, the expectation values of the spin aren't going to be their full values, as it would be if they were uncorrelated states and you just had a single spin pointing in some direction. But there will be a non-zero expectation value of any spin, and that expectation value will be the exact opposite at state n plus 1 as at state n.
The flip doesn't have to be 180 initially, right? I mean, it could be a little.
Well, like I said, 170 or whatever, yeah. And
does that break down at some point?
Yes, at some point when it's too large, this is going to break down. You will go through a phase transition, and eventually you'll go into another phase where it all wipes out. Okay? But the Hamiltonian, even here, the Hamiltonian in step 1 is only rotating by 170 degrees, and then followed by and although the Hamiltonian is only doing 170 degree rotation, followed by the interaction, the state of the system is doing exactly 180 degree flip. Okay? So the system is self-correcting, even though you're not tuning to make it go exactly flipping by any amount, but the interactions of the system, because the spins are not independent, are self-correcting it.
Setting conditions on the time, T naught, and some scale must be there, right? How long you go on T naught relative to the interactions and things like that.
That's right. So it's very good. So the interactions certainly need to be large enough, okay? And so there's a couple scales there. There's the strength of the interactions times T naught, which is a dimensionless quantity. And then there's also the variation of the pulse from pi over 2, which is another dimensionless quantity. And so those dimensionless quantities have to satisfy certain conditions, okay? So the first dimensionless quantity needs to not be both of them basically need to not be too large, okay? If either one gets too large, you cross some phase transition. Okay. Okay. And again, this is analogous to the crystal state of methane on graphite. It's opposite at even and odd multiples of T. It's like saying that there's different probabilities on half of the sites as on the other. Neither of these probabilities is necessarily 0 and 1. It's not like they're all the time on some sites and never on the other sites. It might be like 75% probability here and 25% probability here. Similarly here, if I look at any spin, its expectation value is not going to be plus or minus 1. Its expectation value might be like 0.6 or something, but then it's going to be minus 0.6 at the next step. Okay? Okay. So the oscillation self-corrects so that it rotates by exactly 180 degrees. As it would if So that kind of out-of-phase piece gets damped out. Okay. Now, it's easy to see how this could happen in a simple soluble model, because if you take a system in which that Hamiltonian has no sigma x terms, okay, so you can just diagonalize it, then you can show, just by diagonalizing this, the part that happens during the second interval, you can find the eigenstates, and then use the eigenstates of that Hamiltonian to find the eigenstates of the Floquet operator, and it turns out they are just superpositions with known coefficients of an eigenstate of that Hamiltonian and another eigenstate with all the spins reversed. Okay? And it turns out that's a cat state, because those are states that differ by macroscopic flip, and the corresponding eigenvalues differ by an overall sign. So this is exactly what you would expect according to our second definition of time translational symmetry breaking. Now, of course, this is for some particular fine-tuned soluble limit. Okay? And you're going to ask, is this a stable phase of matter? Okay? Well, the answer to this is, whether this is a stable phase of matter, is subtle, because oftentimes what we normally do is we try to find the ground state of a system. We say, OK, we'll go to some soluble point. We find the ground state or ground states at that soluble point. And then we're going to say, OK, we'll perturb away from that soluble point. And if that perturbation is small, then we can do perturbation theory. And if we have a ground state with a gap, then if the perturbation is small compared to that gap, the perturbation theory will be small. And then we have a chance of getting the right answer. But you see, we're not talking about ground states. We're essentially talking about generic states here. We don't have a gap protecting us. All these states are very close, exponential. The splittings between eigenstates are exponentially small in system size. We're not even in a static system that would have a ground state. We're in a Floquet system where you're living up here with just generic states. So finding a soluble point is great, but it doesn't get us home, because we can't then just do perturbation theory, not easily, because we don't have a gap. Okay? So stability to perturbations is not guaranteed. But it turns out that stability to perturbations is actually due and is synonymous essentially with crypto equilibrium. What it turns out is that there exists some unitary transformation such that we can turn the Floquet Hamiltonian into a Hamiltonian of the Floquet operator into a time translation operator of the form like this, which is a perfect pi pulse times evolution under some Hamiltonian that commutes with that pi pulse, which you'll recall that is exactly the form of our exactly soluble point. So there exists some unitary that lets us turn it into that exactly soluble point. Now, normally, we're doing perturbation about the ground state. We find one way to think about perturbation theory is that you're finding a unitary transformation that maps the eigenstates of the perturbed problem onto the eigenstates of the unperturbed problem. That's one way of thinking about perturbation theory. Turns out that same idea can be used here. Is just that we can't rely on a gap to justify such a perturbation theory. That's kind of an unfortunate place for that. If I click this, is this going to turn everything off? We know how to move this. Anyway, OK. What's missing here is this is basically the change in the Floquet eigenstate due to some perturbation. And the reason that there's no obvious, that this perturbation theory may or may not succeed is that these eigenvalues aren't particularly, the differences aren't particularly large necessarily. However, in many body localization, the interesting thing is that eigenstates that are nearby an eigenvalue are necessarily far away in space. That's kind of why the system manages to be localized. And so therefore, local perturbations actually don't have any matrix elements between states that are nearby in energy, which you can think of as saying that there's no resonances. As a result of which this perturbation theory can be rewritten in a non-singular form that lets you transform the eigenstates of the perturbed system into the eigenstates of the unperturbed system. And this is just local unitaries that can't transform the cat states that are eigenstates of our time crystal at the soluble point into non-cat states, which would be on the other side of the phase transition. And the implication is that there's an alternating basis in which this looks like a static system, which is just a basis that's rotated by u. Okay? And on every alternation by x. Okay? So if I just look at even multiples of the period, it actually just looks like time translation under some time-independent Hamiltonian d. Okay? Now, that can also be checked numerically. So one thing we can do is to check that the eigenstates, the Floquet eigenstates are cat states, we can compute the mutual information between distant regions. In the Floquet time crystal state, that should go to log 2. Okay? And what you can see from this scaling form is that indeed it is close to log 2. And then as you crank up h and it approaches the phase transition, it goes towards 0, as it should be outside of the phase. And if you do a finite size scaling on this, in the limit as these get far apart and each of the regions get larger, this is the part of the phase diagram where the Floquet eigenstates are cat states. Okay? You can also, and this was done by work by Norm Yao and collaborators, you can look at the phase transition. So you can remember that you have this approximate pi pulse. You can make that approximate pi pulse like 170 degrees and so on, and move further and further away. And it turns out that the transition out, when you look at this mutual information, collapses onto the form of just a randomizing model. Okay. We can look at the time dependence, start at initial state, and look out in time. And what you can see is if you were outside of the time crystal state, basically if I look at sigma x, sigma y, sigma z, they all kind of have a transient and decay way. Whereas if you're in the time crystal state, the sigma y and sigma x decay, but sigma z is just alternating like this. And those alternations continue on for many periods. This was done by TEBD, which let us do larger systems but for shorter times. And then if you looked at smaller systems but for longer times by exact diagonalization, then you can see that as the system size increases, the length of time over which these survive increases exponentially with system size. Okay? So because this is a log scale, so the oscillations persist to exponentially long times in system size. I'll contrast that with, for instance, Rabi oscillations, which again, if I put a field in some direction, you see some oscillations. But if there are initial states for which there are no oscillations, and that initial state can be prepared efficiently. Also, if I made a small change, if I changed the size of the magnetic field by 5%, then I end up changing the period from 1 period to 20 periods. So this has no rigidity associated with it. Whereas what we're talking about has this rigidity. Okay. So it looks like I'm coming to the end of my time. Let me just very quickly say, what I just discussed is how MBL, many-body localization, prevents the energy absorption. As I said, there's this other route to a time crystal through prethermalization that also suppresses the energy absorption and delays heating. Okay? And it turns out this can occur in 1D with long-range interactions, okay, or in D greater than 1 with short-range interactions, so long as the interactions are weak compared to the time, the period over which you apply that interaction, which is what we mean. So prethermalization is something that occurs in the high frequency limit. That is what high frequency means, okay? Which is that the part that's not a pi pulse should be a very small, almost one unitary transformation within each period, okay? I'm going to kind of just skip through some of these details and just, given the time, quickly mention the experimental realizations. Okay, so here's a realization with trapped ions. Okay, this is ytterbium ions. This is Chris Monroe's lab in Maryland. And what they saw was they were able to allow to apply approximate pi flips and then allow them to interact. And they saw that without the interactions, you can see that by changing, going a little bit away from pi flip, you split this peak so you're not exactly doing, the system was not just doing in long times the pi flips, whereas with the interactions on, you stabilized, when the interactions were strong enough, you stabilized, even though you were not doing an exact pi flip, you stabilized the system so that it actually, the response of the system was at period pi, okay? So it's a time crystal when the interaction is strong. But unlike in our simulations, it's not quite exponentially long-lived for reasons, one having to do with relatively small system sizes, for which there are some ways around that having to do with prethermalization, and for also reasons that are not fully understood in the experiment. Okay. Another realization, this is Misha Lukin's lab in Harvard, NV centers in diamond. So this is diamond with a lot of a high density of these defects. NV centers, sometimes called black diamond. And again, a very similar protocol to the previous experiment and a pretty similar looking result. Okay, where again, if the interactions are weak, you don't see, you see beating, which is characteristic of a frequency that's not locked to anything, whereas when the interaction is sufficiently strong, you're locked in at this frequency at which the system self-corrects. Although the signatures are similar, the system is actually quite different. The previous one, as I said, was trapped ions. It was a 1D chain. This is a 3D system with dipolar interactions. So a lot of the details are different, but a lot of again, the basic phenomenon seems quite similar. Okay. So I talked about time crystals. It turns out in crypto-equilibrium there are other interesting driven phases. It turns out there's topological phases and symmetry-protected topological phases that are classified by the way in which the time translation symmetry is realized. There's phases with protected edge modes and so on. So I'll just leave you with an outlook that we're now, I think, sort of seeing that periodically driven systems have a rich phase structure in certain cases having to do with many-body localization or prethermalization that look just like what you have in equilibrium systems, but with some possibilities that you can never see in equilibrium. Okay. With that, I'd like to thank you for your attention and take questions. Yeah.
So in 1D, I also can imagine domain also solitons, which would propagate through the system, and at any finite temperature, there will be a finite density of those which would break translational symmetry. So why doesn't it occur here? Why don't you have solitons that propagate in the system, and that would split from odd, even to even odd, even odd?
Yeah, that's a good question. So the answer is in the many-body localized case. Okay, so there's two different answers. So in the case of many-body localization, many-body localized systems, even far up in the spectrum, actually look like ground states. So it survives for the same reason that the quantum 1D transverse field Ising model has an ordered state at 0 temperature. The physics is very similar to that of the quantum transverse field Ising model of 1D, that they act like 1D systems. Now, for the case of prethermalization, okay, that actually it's not necessarily a 1D system. That works outside of one dimension, and like the black diamond experiment of from Lukin's lab is a 3D system. So it survives for the same reason higher dimensional systems are stable, because high dimensionality suppresses fluctuations. In the prethermal case, it turns out that you can also stabilize order in 1D with long-range interactions. So the ion system has a power law interaction, and that power is actually pretty low, and that power law stabilizes the order as well. So it's like an Ising model with long-range interactions in that case.
But you're saying in the case of the usual short-range Ising model, you will have the solitons that would break the crystals, the time crystal.
If you have a prethermal time crystal in one dimension with short-range interactions, it will not have long-range order. If you have a many-body localized, it will have long-range order because it effectively is sitting at 0 temperature, even high in the spectrum. Yes?
I've noticed that this kind of whole field of MBL topics has kind of blown up over the past few years. You can see a good direction for students looking for like a area to focus on. It's a good direction to go in.
Well, I would say MBL itself might be a little too narrow a focus because I think a lot of the low-lying fruit were already kind of hit sort of in the last 5 years. There was a lot of activity. But I would say that MBL was kind of the gateway drug towards thinking about quantum non-equilibrium, far from equilibrium quantum systems. And that's a much broader area that I think is a good one to go into.
Other questions? So I have one question, and I was wondering how relevant your reference to the Rabi oscillations were, that you said that by tweaking you can change the period.
Oh.
But that's a continuous symmetry you're trying to break.
Mm-hmm.
The example you gave, you're breaking a discrete symmetry, which
Mm-hmm.
is, of course, much harder to break. So,
Mm-hmm.
I mean, in that sense, is that just an artifact of the fact that, you know, is that a straw man in the sense that
No, so
breaking continuous symmetry is much harder than all that stuff meant?
no, I don't think so. Because if you look, for instance, at experiments like these, what you can see is when you're not in the time crystal phase, if you change the frequency a little bit, if you change the pi pulse to an approximate pi pulse, you can see you have this beating, which is just telling you that actually the period has been changed by a large amount. The true period of the system has been changed a lot, basically continuously. These peaks are split by a continuous amount. Whereas in the time crystal phase, as you vary the length of the pulse, actually the peaks don't split. The peak doesn't split. So I think this is exactly like that, even in the discrete case.
All right. No other questions? Let's thank Chetan.
Thank you.